I have two problems here working on graphing quadratic functions. And this is in standard form. Remember, we can read the vertex off really easily here. This is in general form. That is typically easier for factoring, for finding those zeros or those x-intercepts. Okay, so the nice thing about standard form, remember, I went ahead and used z as the variable. We're going to try and be comfortable, both of us, with using something besides x for the variable. What we have here is z minus the x-coordinate of the vertex. So this is z minus -1. And then this is the y-coordinate of the vertex, so that's 3. You can read off of the lead coefficient whether this is cupped upwards and downwards. So really, if you were wanting to graph this right now, you could actually do it just with these pieces of information. Let's see, at -1, 3, that's your vertex, and it's cupped downward. And this -3 says if I move 1 to the right or 1 to the left, I'm going to go down 3, down 3. So 1 to the right, down 3, 1 to the left, down 3. That's what my parabola is going to look like. Remember, the lead coefficient tells you if the lead coefficient is positive, it's going to be cupped upward. If the lead coefficient is downward, it's going to be cupped. If the lead coefficient is negative, it's cupped downward. So we've got a shape, we've got it pretty quickly in standard form here. Well, what else can we see about this parabola? This is about graphing them. Well, notice that this is totally symmetric about that line. That's called the axis of symmetry. And if you know what the vertex is of a parabola, the axis of symmetry is just x equals that coordinate. That line is x equals -1. Okay? You could also probably read off some other pieces here. You could read off the domain. Well, what limitations do you have on inputs here? What could you put in for z? If you're thinking to yourself anything, you're absolutely right. The domain here is all real numbers in interval notation, -∞ to infinity. The range isn't quite that broad. Notice, remember, the domain is sort of where the shadow would be if a light was shining from above. The range would be if lights were shining towards the y-axis, what would be the list of possible outputs? Well, you could be as small as you wanted, but you can't get above 3. So the range is -∞ up to 3, including 3. So we have that square bracket. So that's what we have there. Now, let's imagine you know that this is the vertex, but you're just sort of having trouble internalizing that. Or you know this is what you're supposed to do when you move right or left 1, but you're having trouble internalizing that. You want to take a problem or two and just sort of slow down and actually plot the points and see where that comes from, okay? So I say that the vertex is at -1, and at -2 and 0, we're going to be down 3. But let's just, I think, to me, getting comfortable with seeing how that works helps you to remember it. What happens if you plug -1 in there? Can you see that what happens is this gets to be its smallest possible magnitude? You plug in something that makes this term 0. That means all you get out is that, right? So we get the point -1, 3. Now, if you go one direction, either direction, one unit either direction, can you see that the squared makes it do the same thing? So if I put in 0, I get 1 squared. So I get an extra -3. 1 squared is 1, -3 plus 3 equals 0. So I go down 3. But the same thing is true if you plug in a -2, because that squared makes it so it doesn't know that's not a positive 1, so you're down at 0, so -2, 0. So hopefully that sort of gives you an idea. If the lead coefficient were 7, these would be 7 higher than the vertex. That's the way it works. Okay, let's look at this in general form. Now, general form is better when you're looking for the x-intercepts or the zeros. And you probably remember that the way you do that, right, x-intercepts or zeros are where the output is 0. We're starting with a y value. And then maybe I'd factor out a 2. And then I'm coming up with two numbers that'll multiply to -4 and add to -3. So I'm sort of stuck with 1 and 4 and 2 and 2. And I think I've got the best shot at 4 and 1. If 4 is negative and 1 is positive, those are going to multiply to -4 and add to -3. So that's my factorization. In other words, x equals 4 and x equals -1. Those are the values you could plug in here to get an output of 0. So if you're graphing that, sort of what you want to think about is you want to think about 1, 2, 3, 4. Those 2 points being there. Now the lead coefficient is positive, so we know generally speaking, we've got a picture that looks like that. Now, where's the vertex? It's harder to know over here. It's easier to know those intercepts, those x-intercepts, but the vertex is a little harder to know. There's sort of 2 different approaches to finding where that vertex is. The easiest one in my mind is to start out by finding the x value of the vertex. And the x value is always going to be at -b over 2a. So there's an interesting way to see that. So the x value is at -b over 2a. The way that I see that is, imagine you use the quadratic formula and found these two. Well, if you'd use the quadratic formula to find these two, one would be -b, let's pretend like this was the -b plus square root of b squared minus 4ac all over 2a, right? And then this point would be -b minus square root of b squared minus 4ac all over 2a, right? Well, if this is -b over 2a plus junk, that's -b over 2a minus junk. And this is exactly halfway. Can you see that? This is just that first piece in the quadratic formula. So if you have the quadratic formula, you get this for free. Life is great. So in this particular problem, b is -6, so -6 over 2 times a, that's 4, 6/4 is 3/2. And, you know, I was sort of cheating because I made the problem, but you can sort of see the vertex, the x values at 3/2. Well, how do I find the y value of the vertex? Well, if I know the x value and I want to know how high the function is anywhere, you just plug that in. You just plug in f of 3/2. And you can do that. I did it ahead of time just to save time. I believe it's -25/2. But you just plug that value in here. Okay, so the vertex is going to be at 3/2, -25/2. So that's a real nice strategy. Now let's just imagine, for the sake of argument, that you wanted this to be in standard form. There are actually some occasions where you might want that to be true. If you wanted this in general form, probably most people know how to do that. You simply square this term and then distribute the -3, and it's in general form. It's a little trickier to take this and put it in standard form. Now, the nice thing about this is, now that we know this piece here, we can basically cheat. Since I know this picture, I know what the right answer is going to be over here. Let me make sure I give myself lots of room, but I know it's going to be, I know what the lead coefficient is, right? It's 2. And I know the vertex is at x minus 3/2 squared minus 25/2. So there we go. That's the answer. But there's a process besides sort of the graphing process. This is called completing the square, and it comes up actually in a bunch of other areas, so it's worth taking maybe 2 minutes to to see it. Okay, the first thing I'm going to do is factor out the lead coefficient. Okay, I'm going to factor it out of all the x terms. And now I'm going to put in there the thing that will make my piece inside the parentheses a perfect square. What's that going to be? It's going to be this term divided by 2 and squared. So negative 3 divided by 2 is negative 3 halves. And I'm going to add that thing squared. Okay? So negative 3 halves squared. Now you can't just add something and say that it's equal. But you can add something, then subtract the exact same amount. Well, let's be careful. Let's see exactly how much I added here. I added 2 times this. And this is, let's see, if you squared that, that would be 9/4. Twice that would be 9 halves. So I have to subtract 9 halves. Fair enough? So why did I do that? Well, the whole idea of completing the square is you can check. This is exactly x minus 3 halves times x minus 3 halves. We built it that way. That's exactly what happened here. And then this piece is negative 25 halves. Isn't it amazing? Exactly the answer we were looking for. You could always use completing the square to find the vertex as well.